if I were to do this on my own, this would have been a complete waste of time. That's the reason why I need the feedback. Because I would have probably spent about 30 minutes just recording it, and there would be no sound. All right, so sometimes happens. All right, so that was actually good feedback. All right, so inductance. Start all over again. All right, so it's mutual induction. This is the first thing that we will do. So you got a primary and a secondary coil. We're trying to create current in the secondary coil. Primary coil is hooked onto an AC generator. So what's happening is it's got this alternating current or the variable current, right? So the current not only is changing direction, but also its value, the magnitude keeps changing. So the alternating current or the changing current or variable current is going to create an alternating magnetic field, changing magnetic field, variable magnetic field. And notice that this magnetic field generated by the primary coil is being intercepted by the secondary, right? And the value of the amount of magnetic field intercepted by the secondary coil keeps changing. All right, so that change in value of the magnetic field intercepted by the secondary is what generates current in the secondary. All right, so it's going to induce current in the secondary. So that's the Faraday's law. All right, so we'll get back to this shortly. Mathematically, here's how we model this. All right, so the current within the primary is going to create a magnetic field, circulating magnetic field. So some of that magnetic field is going to be intercepted by the secondary. If we have an alternating current, it's going to create an alternating magnetic field. So which means that not only the direction of the magnetic field is going to keep changing, but also the value. So the strength of the magnetic field intercepted by the secondary coil is going to keep changing, right? So that variation within the strength of the magnetic field intercepted by the secondary coil is going to induce it. It's going to induce a current within the secondary. All right, so the flux, the magnetic flux in the secondary will depend on the current within the primary. So the magnetic flux within the secondary through each and every single turn is going to depend on the current within the primary. So it's going to be proportional to the current within the primary. All right. So in order to turn this proportionality into an equation, we have to introduce a proportionality constant into this mix. The proportionality constant that we get to use is M, that stands for mutual inductance. It's going to have the units of Henry. H stands for Henry. What this represents is, this tells you what portion or proportion of this current is going to be responsible for this flux within the second. That's it. All right. Obviously, not what portion of this current within the primary is going to be responsible for the flux within the secondary. The current is going to generate a certain amount of magnetic field. Not all of that magnetic field is going to be intercepted by the secondary, right? Maybe about 30%, maybe about 20%, maybe about 10%, maybe about 80%. It depends on the geometry. Depends on a bunch of factors. So M represents literally the amount of current which is going to be responsible for the flux within the secondary. That's what it means in essence. All right, so this is the basic setup. So what are we doing? We were varying the current within the primary. All right, so this variation of the current is going to change the flux within the secondary through each and every single turn. And only a certain portion of the current is going to cause, it's going to cause a change in flux within the secondary. Change in flux within the secondary is going to cause an electromotive force within the secondary. So this electromotive force is going to be responsible for the current in the secondary. That's it. So this is a re-expression of the Faraday's law. All right, so we rewrite the equation. It's going to look like this. So changing current within the primary is going to cause a change in flux within the secondary. And change in flux within the secondary is going to cause an electromotive force in the secondary. That's it. All right, so that's the mutual induction. All right, the second one is the self-induction. Concept is the same, except this one is a little bit more interesting. So mutual induction, in essence, is the same as transformers. Okay, so this one is the one that we will focus on a little bit more when we're dealing with more sophisticated circuits, like the RLC circuit. All right, so this is the one that requires a little bit more attention to detail because there's going to be a self-induction. All right, how does that go? We got our AC generator, meaning that we're creating an alternating current, meaning that not only are we changing the direction of the current, but also we are changing the magnitude, the size of the current. So we know from Earth that the current creates magnetic field, so it's going to be responsible for it. And the magnetic field created by this current, it's just going to loop around. All right, so this is the magnetic field created by this current. So it's not only leaving this region, but it's also just looping around and entering back into this region. All right, so the value of the currents is changing, the direction of the currents is changing, which means that the value as well as the direction of the magnetic field generated by this occurrence is changing. While this magnetic field, which is generated by this loop, is also the same magnetic field which is being intercepted by the loop itself. All right, so any variation of the strength of the magnetic field intercepted by the loop at this end is going to induce a current which is going to try to oppose any change of magnetic flux. So the Lenz's law is going to kick at some point. So which means that this self-induction is going to make this inductor act like some kind of a variable resistor. All right. Once again, the crucial information is the magnetic field generated by this coil is also being intercepted by this coil. All right. And so it's generating a variable magnetic field because the strength of the magnetic field is changing inside the loop, which means that there's a change of flux here. And when there's a change of flux, it's going to induce a current, which is going to move in a direction that's going to oppose any change of flux. So if the current is increasing in this direction, there's going to be an induced current, which is going to try to oppose that change. So the induced current is going to move in the opposite direction. All right. So this is known as self-induction. All right. So mathematically, the concepts are identical, or the derivations are identical. All right. So this current is going to be responsible for the flux, the amount of magnetic field intercepted within this region, within the area of this loop. All right, and so the flux through each and every single turn is going to be proportional to the amount of current that you're looking at. Once again, you got this proportionality turned into an equation. You need to have a proportionality constant. So L in this case is self-induction, expressed in terms of Henry. And instead of saying self-induction, we just say induction. It's the same thing. And this is an inductor. All right, once again, L represents the portion or proportion of the current responsible for the flux through the coil or the inductor. All right, so this formula just is a representation, mathematical representation of what I was describing. So changing current is going to be responsible for the change in flux through each and every single turn. And changing flux is going to be responsible for the electromotive force. And this is otherwise known as the back EMF. So which means that the induced electromotive force is going to act in a direction to oppose any change of flux. All right, so that becomes the expression of the Lenz's law in essence. All right, that's pretty much it. All right, so that's the derivation. All right, so speaking of induction, self-induction or mutual induction, regardless, that represents the amount of current or the proportion of the current or the portion of the current, which is going to be responsible for the flux in the secondary. All right, so what does that depend on? All right, so this derivation is going to give us the answer for that. All right, so here's a basic statement. The current is going to be responsible for the flux. L represents self-induction or induction. All right, so isolate L here. So we're trying to come up with a mathematical expression for it. So the flux is the amount of magnetic field intercepted by the area of the coil. The magnetic field in this case is the magnetic field within the coil itself. This is a solenoid. So this represents the magnetic field of a solenoid. All right, so do a back substitution here. And then do a back substitution here. As a result, we end up coming up with this expression. So the current doesn't matter. So the inductance does not depend on the current. And looking at this, it's fairly obvious that it's going to depend on the geometry. So it's going to depend on the area of the loop. And then it's going to depend on the number of turns per unit length. Somehow, this is number of turns, this is number of turns per unit length. And then what we can do is we can combine number of turns per unit length and number of turns using this equation. So in this case, I'm expressing everything in terms of number of turns per unit length. So what does that depend on? It depends on the number of turns per unit length. So the larger the number of turns that you have, the bigger the inductance. The longer it is, the bigger the inductance is. What else? The larger the cross-sectional area of the loop, larger the area of the loop, the bigger the inductance is. That's it. So it's kind of common sense. Longer it is, larger the inductance. So larger the area, bigger the inductance. More wires that you loop around, bigger the inductance. So that's it. Those are the parameters that it depends on.
An electric current in any circuit creates a magnetic field which, whenever it changes, induces a current in the same circuit that opposes the change. This phenomenon is called self-induction. The effect of self-induction is larger in a coil of many turns, called a solenoid, precisely because it loops many times around the changing flux. That's why a solenoid is used as a symbol of self-inductance in an electric circuit, where an inductor may be an element like a resistor or capacitor.
Current increasing in an inductor causes an opposing electromotive force, according to Faraday's law. And since the flux is proportional to the current that creates it, that electromotive force is equal to minus a constant L times the rate of change of current. L is called the inductance of the circuit element. An inductor opposes and slows down the buildup of current in a circuit, while a resistor may cause the current to decay by dissipating energy.
All right, so that little video is describing that. So the induced electromotive force is going to oppose any change in current, in essence. So if you're increasing the current value, the induced electromotive force, which is known as the back EMF, is going to try to cancel out that increase. If you're decreasing it, once again, it's going to act in a direction to oppose that decrease of current. All right, so RL circuits is one of the circuits that we are focusing on. All right, so you got your power generator here. So the current is going in this direction. And as soon as you start to build up the current, the inductor is going to act to oppose that increase in the current. All right, so what that means is the current is going to gradually build up. The voltage is going to gradually build up. The current is going to gradually build up. All right, so that in this case, the voltage is gradually building up. When you introduce a battery into the system, and when you remove the battery from the system, the voltage is going to gradually go down. All right, so the voltage gradually builds up, the current gradually builds up, the voltage gradually goes down, the current gradually goes down. So that's what it means. All right, so mathematically, the only thing that I'm interested in from this section is if the current is gradually building up, this is the formula that we get to use. Tau here is going to represent the inductor time constant. This represents the how fast or gradually the current is going to build up. That's the meaning of it. So the larger the inductance is, the longer it's going to take. The smaller the inductance is, the shorter it's going to take. I think that's an interpretation. All right, so when you remove the battery from the system, all right, so the current is going to decay gradually. Once again, this is the formula that we will get to use. All right, so I sub 0 represents the maximum amount of current. So this is your maximum amount of current within the circuit, so it's gradually going to diminish. It's going to gradually go down. Once again, I sub 0 here represents the maximum amount of current that you can have within the circuit. All right, so the example problems, like you have problem number 3, the problems in this section are not that complicated. So my recommendation is just take a look at a problem like this. That's one of the problems that I'm going to recommend. And we'll get back to the problems that I'm going to ask you guys to focus on. The second circuit that you can build is an LC circuit. This is an inductor capacitor circuit. All right, so capacitor is built up, it's charged up completely. And then you place the capacitor inside an inductor circuit. It just has an inductor in it. So capacitor is it's going to act like a battery in this case. So it's going to discharge, and then it's going to charge up, it's going to discharge again. So this becomes, all right, so this is, and then it reverses itself. All right, so it's charged up, it discharges, and then, okay, so it's going to charge up again, and then it's going to discharge, and then it's going to be at this point. So it turns into some kind of a cyclical process that we're looking at. All right, so the energy is going to be stored within the capacitor originally, and then the inductor is going to put the brakes on. So this is discharging. Inductor is going to create an electromotive force. It's going to oppose that change. So it's going to slow down the process, and this thing is going to gradually charge up again. And then once again, it's going to gradually discharge. And then it's going to gradually charge up again. It's going to gradually discharge. And it's going to gradually charge up again. It's going to gradually discharge. So that's what's going to happen. So there's a cyclical process involved. All right, so initially it's charged up. Okay, so this is a better representation. So capacitor is charged up. And then it starts to discharge. Inductor is going to put the brakes on, in this case. and then it's completely discharged. The current is inside the inductor, is going through the inductor. So the capacitor is going to charge up. It's fully charged. Now it reverses direction. So what's happening is the energy gets transferred between the capacitor in this case. So the energy is stored within the electric field of the capacitor, and then eventually it's going to be fully stored within the magnetic field inside the inductor. So the energy is going to get transferred back and forth, back and forth. So we end up getting this cyclical process. So this is a single cycle. Now, the number of times it does this cycle is known as frequency. All right, so if the frequency is like 10 hertz, it's going to charge and discharge 10 times per second that we got. All right, so the couple of things that we're going to be interested in for the multiple choice problems per se are a few formulas that we need to focus on. That frequency that I was discussing, like the number of times this thing charges and discharges, is known as the natural frequency of a system. Natural frequency is something that we discussed yesterday. All right, so which means that the circuit is going to oscillate naturally at this frequency. All right, so this is the natural frequency of the system. It's going to depend on L, it's going to depend on C. Okay, so the larger the inductance is, the lower the frequency is going to. Okay, so why is that? Because the inductance is going to slow down the process. All right, so it's going to slow down the discharge as well as the charging out process. Charge and discharge is going to slow down. That's what it is. Larger the capacitance is, the lower the frequency is going to be, because larger the capacitance is, more charges you can put on a capacitor. So it's going to take longer to charge it up, in essence. All right, so that's one of the things out of that. The second thing is the amount of energy stored inside a capacitor. All right, so the total amount of energy stored inside a capacitor, excuse me, is going to be that formula. Let's get back to it again. Just stop now. That's the total maximum amount of energy stored inside, not a capacitor. The maximum amount of energy stored within the circuit is the same as the maximum amount of energy stored within the electric field of a capacitor, which is the same as the maximum amount of energy stored within the magnetic field inside a inductor. This is going to be given by this one. All right, so those two formulas are important. And we will get to utilize these formulas when we get to the RLC circuits. They will form the foundation of the lecture on RLC circuits. So also on top of that, of course, you will have some multiple choice problems that will require that you know how to use those formulas. All right, so speaking of being able to use formulas, all right, this is a couple of things to focus on. Problems are straightforward in this section. All right, guys, there are 4 problems. All of them are important and all of them are real easy. Okay, so my recommendation is just find problems like these. All right, so I don't have the solutions per se, and I don't really have too much time to solve these problems and put them up. And these are standard physics problems. You can find problems like this in just about every single book. All right, so the problem number 2, for example, figure out the self-inductance. Length is given, the cross-sectional area is given. It contains this many terms. Pretty much. This one is straightforward. This is almost like, I don't know, multiple choice test question. So it's the first one. All right, so you can figure those out easily. All right, problem number 3 is more like a show work problem. All right, this is not that complicated. It's doable, but the quality of the test question is going to be along these lines. So you got an RL circuit connected to a battery, so it's just charging up, the current is building up. So the amount of time it takes for it to reach out of this value. So, all right, so that's completely doable. Question number 4, you got a solenoid. Once again, the inductance is given, the resistance is given. So once again, this is an RL circuit. So the amount of electromotive force applied is given, so that's your voltage. So how much energy is stored in the magnetic field after the current value is built up to its equilibrium? All right, so what is the amount of energy stored and how many time constants? All right, so the amount of energy stored within an inductor is something that you will have to look up.
Mr. Kenneth?
Yeah.
Yeah, I gotta go to another class at 10. Did you go over the conceptual stuff already?
No, not yet. Which I
Okay.
will in a second.
All right. You posted this, right? This video?
Yeah,
Okay. Thank
I
you.
will. All right, so the energy stored in a inductor, this located right here, All right, so you can figure out the amount of energy stored in an inductor. All right, so this is the formula that you have to use. So L is given, figure out the current out of that. And you should be able to do that in terms of solving these problems. All right, so this is the amount of energy stored in an inductor. Energy stored in an inductor. So this is the formula that you have to use for that. Not that I didn't have that. All right, so just figure those out. All right, so lastly, I got like 5 minutes. Let me just go over the questions. All right, so the question number 1, we got a current in a circuit containing a coil, so that's an inductor, resistor, and a battery. And the current reaches its constant value. So does the coil affect the value of the current? The answer to that question is absolutely not. If the current reaches its constant value, if the current is not building up, or if the current is not decaying, if there's no change in current, then the inductor is going to have no effect on the current. The inductors work with changing currents. If the currents are changing, the strength of the magnetic field produced by the current is going to be changing, which means that the amount of strength of the magnetic field intercepted by the coil is going to be changing. So that's going to cause a back EMF. And so that the back EMF is going to act to oppose any change in flux. So it's going to oppose any increase or decrease of the current value. So what parameters affect the inductance of a coil? Okay, it's the geometry. It's the length of the coil. Obviously, it's the size of the area of the coil. It depends on the number of turns that it's going to have, and those are the parameters. So it's the geometry that affects it. So how does the metal detector work? Well, the metal detector works in a way that you get this inducting coil. You got the transmitting coil. You got buried gold in the ground. Transmitting coil is generating an AC current, obviously. So you got this alternating magnetic field. And the magnetic field is being intercepted by the buried metal, in this case, gold. If you vary the strength of the magnetic field inside the gold, it's going to cause a circulating magnetic field. And it's going to cause a circulating current. It's going to induce a circulating current. So the circulating current is going to it's going to cause a circulating alternating current. Let's put it that way. So the current generates induces its own magnetic field. The current generated by the gold coins is alternating current, so which means that the magnetic field is going to alternate in direction as well as magnitude, which is going to be intercepted by the secondary coil. If the magnetic field, the strength of the magnetic field is varying, intercepted by the secondary coil, is obviously it's going to create a current in the secondary coil. All right, so secondary coil is at 90 degrees to the primary coil. The reason why it is solved so that it's not intercepting the magnetic field generated by the primary coil. All right, so which means that it's designed to only intercept the magnetic coil, a magnetic field generated by an external source. All right, so how do you increase the voltage in the secondary coil of a transformer? You increase the voltage in the secondary coil of a transformer by increasing the number of turns in the secondary. And the reason why that's going to work is because the change of flux within the primary and the secondary is the same. All right, so the change of flux within the primary and the secondary is the same. And because the change of flux within the primary and secondary are the same, if you increase the number of turns in the secondary, it's going to increase the electromotive force in the secondary. So the question is, why is the change of flux in the secondary is the same as the change of flux within the primary? The reason why the change of flux in the secondary is the same as the change of flux within the primary is because the magnetic field is generated by the primary coil is pretty much contained within the iron core. All right, so for this to work, you have to have an iron core, and then the iron core is going to be able to contain and redirect the magnetic field through the secondary coil. So the change of flux within the primary is going to be the same as the change of flux within the secondary. So if you increase the number of turns in the secondary, that's going to increase the electromotive force in the secondary. All right, so explain how they explain current in the secondary coil using a primary coil. This is gibberish. Explain how to generate current in the secondary coil. It should say. All right, how to generate current in the secondary coil using the primary coil. All right, so this is the mutual inductance. All right, so the current within the primary is going to be responsible for the flux within the secondary. So if you change the current within the primary, it's going to change the flux within the secondary, and then the change in flux within the secondary is going to induce an electromotive force in the secondary. And the electromotive force in the secondary is going to drive the current in the secondary. All right, so that's pretty much it. All right, guys, I have a lecture, so I have to just move on.
Does current matter for number 2 on, you said geometry, but does current matter on?
All right, say again.
Does the current matter on number 2?
It
You
makes
said
no. The current doesn't matter.
Current
no,
does not matter.
Current matters nothing. The only thing that matters is geometry. Okay, so you have the term inductance. It's a proportionality constant. What that means is it tells you what proportion of the current which is going to be responsible for the flux in the secondary. All right, because the magnetic field which is generated by the primary is not contained inside an iron core in this case. Only maybe about 30, 40, or 50% of it is going to be intercepted. Certain proportion of it is going to be intercepted by the secondary. So L is that proportionality constant. All right. So it only depends on the geometry. The longer it is, the larger the inductance is going to be. Obviously, the more turns you have, the larger the inductance is going to be. Larger the area of the coil is, the larger the inductance is going to be. That's it. So it strictly depends on geometry.
All right, thank you.
Okay, no problem. All right, guys, I have to go. Once again, any questions, just email me. All right, take care.